So now we're zooming out, we're starting to consider the shapes of objects and learning how to find their centers of mass. Now you might wonder, how did we get away with it for so long, being able to consider objects as point masses and able to defend the physics that we do? I'd like to show you that right now. Let's get started. On the screen you see the center of mass equation in one dimension that you've gotten familiar with. What I'd like to do is differentiate this with respect to time, and in fact I'm going to do it twice. So what I mean by that is I'm going to take the derivative here, okay, of this one with respect to time. Now obviously the masses of the individual objects that make up this system, right, M1, M2, those masses are constant, so when I do that I'm only essentially taking the derivative of the position. My pen's gone nuts on me. So this would look like this. I'm going to pause and write this out, and I'm also going to go ahead and take the second derivative as well. Let's hold off on the second derivative. Look what I've done here, just taking the derivative of each component. Now I think you'll recognize that this, remember the first derivative of position is the velocity. Right, so what we get is essentially this here. Alright, and now we're going to turn around and we're going to do the same thing again, except we're going to take we'll take another derivative with respect to time, okay, or the second derivative of position. Let me pause and write that out. Okay, there you have it, the second derivative of position. But isn't dv dt acceleration, right? So do you see that over here the summation is really m I a I, right? And so what we can write then ultimately is that the acceleration of the center of mass, okay, is the sum of this, all the individual particles. Remember though that we know from Newton's second law that this is equal to that. Okay? In other words, the motions of all those individual objects, okay, acts as if there were just a single external force acting on the center of mass of the system. In other words, we reduce the motion of all those individual particles in the system to F equals ma of this one particle, right, this imaginary particle where all the mass is concentrated at the center of mass. Okay, so that's sort of the mathematical, showing you mathematically that, hey, we can get away with treating a system of particles as if all the mass was concentrated at the center of mass. And we get the same F equals ma equation that we've been using all along. Okay, why is this center of mass so important? Well, let's take a look at some practical examples because it allows us to look at some things that seem to be very complex and allows us to vastly simplify the motion. On the next screen, I do have some examples. I'll talk about them in a minute, but let's consider a simple example first. Let's say that you fire a projectile up in the air, okay? And you know the path of a projectile is a parabola, right? So it's going on its parabolic path, and right when it gets to the top, all of a sudden, unfortunately, okay, let's just make it like a bullet or a shell of some sort, it breaks apart, okay? And all of a sudden you have a piece that's going that way, right? Another piece that's going this way, okay? Well, how do I begin to decipher that motion, right? Because now I've got like two pieces flying opposite directions. What's going on? Well, here's the cool thing. Because the external force on the system, right, which is both parts together, has not changed. It's only gravity, right? It means that the motion of the center of mass continues in its parabolic path. Okay, so you know that the center of mass, even though no mass will actually land there, you know that the center of mass of the system is there because the external forces on the system of the shell never changed. Okay, and you see that in a few other examples here. Let's look at these pictures that I filched from the internet. Okay, in this first example, this person, I believe, is a scientist actually in San Francisco at a museum there. You can see that what he's done is they've attached a light to each end of the bat and then one at the center of mass. And they threw the bat in the air. And what you see here is this right here, okay? That's the motion of the center of mass, which is a parabola, right? When you throw something up in the air, it follows a parabolic path. Whereas the other shapes we don't recognize, but those are the ends of the bat, and they follow a much more complicated shape, right? So if you consider the ends of the bat to be
different parts of the masses of the system. They follow more complicated motion, but we can simplify all of it by just looking at the center of mass. And you see a similar thing here, right? If we look at the diver, okay, there's that parabola, and then here you also see it for the hammer. We've marked it out with red dots versus yellow dots at the end. So it allows us to look at what seems to be complicated motion and simplify it by looking at the center of mass motion. Let's do one example, okay? Pause the video and give yourself a moment to read the example. I've gone ahead and drawn it out. Okay, so you're on this boat with your date, and you want to switch positions. Now again, if we look at this from a center of mass perspective, notice that although you're going to move on the boat, right, and your date's going to move on the boat, and it's going to rock back and forth. If we look at the system of these three objects, right, you, your date, and the boat as one system, the external forces on that system don't change, right? Therefore, the center of mass can't change, okay? Because only forces external to a system can move the system. So when you guys shift positions, the center of mass of the system can't change. So everything, all the objects in the system have to compensate so that the center of mass stays where it is, okay? So what we want to do first of all is calculate, before you do the switcheroo, where is your center of mass, all right? I'm going to pause and write that out. Before I proceed with the math, I should clarify that I'm going to make my origin be the center of the boat, because notice at the beginning of the problem, I have two of our three objects located at the center, right? So that'll make the math a little bit easier. Okay, you see our result, 0.96 meters. Remember, it's you, the boat, and the date, right? So if you just look at you and the date, you would expect it to be a little more than 1 meter, right? Favoring the date a little bit. But remember, the boat's on your side as well, so to speak. You and the boat together, 130. So we favor our side slightly. All right, now we're going to switch. So all I'm going to do now is switch these two around, right? And then I'm going to do the exact same math again, except the positions of the masses has changed. So the center of mass is going to be in a little different place. Okay, you can see I can set it up. I've called this the new center of mass, right, in the new position. Now the date and the boat are at the origin, which is the center, right, and you're 2 meters away. Okay, when we do this, we get 0.64 meters. Okay, that's the location of the center of mass in the new system. But remember, there's no force external to the center of the mass, so from our perspective, that center of mass can't move. So basically, the boat is going to shift underneath you to compensate, and it's going to shift by an amount that's the difference between these two, right? The difference between these two. So what is that? 96. That's a 0.32 meters. So now you can see how we might use the center of mass, the motion of the center of mass concept, to a quantitative problem solving. All right, I'm going to leave you with the following example that I'd like you to copy down and think about. Okay, it's another motion of center mass problem, and it's actually in the book, and we're going to copy down the solution in class next time. But I'd like you to think about it just for now, what you think the solution might be.